Okay, let us now look at the second part of Rice's theorem. Let us once again go to the important definition. Recall that we have called a property monotone if whenever some RE language L satisfies that property, any superset of L, which is also an RE language, must also satisfy this property. Okay. So, if for some recursively enumerable language A, the property is true, we'll take any recursively enumerable language which is a superset of A, this must also be true. So, false less than equal to false is allowed. But once something becomes true, and if we go to a superset, this will also have the property. So, if some language is infinite, any superset is also infinite. If some language is the entire sigma star, any superset of it can be itself only. So, it is also sigma star. So, these are monotone properties. And the opposite properties, language of n is finite, that is a non-monotone property. For example, the empty set satisfies this, but sigma star satisfies this, does not satisfy this, but t is not less than equal to n. Likewise, language of n equal to empty. So, these are non-monotone properties. Rice's theorem part 2 talks about non-monotone properties. So, let us come to the statement and the proof of Rice's theorem part 2. Good. Yeah, so now it says that no non-monotone property P of recursively enumerable languages is semi-decidable. So, I start with the premise that P is not a monotone property. And then I will establish that the set of all Turing machines such that their languages satisfy the property is not only not recursive, it is not even not recursively, it is not even recursively enumerable. Yeah. So, pi is the set of all Turing machines n such that P of L of n, the language of n, is equal to T, true. This is not an RE set. Okay. Now, in order to prove something is not even recursively enumerable, I need a reduction from some problem which I already know to be non-recursively enumerable. So, we will, for example, in this context use the complement of the halting problem. The halting problem is recursively enumerable but not recursive, and therefore its complement is not even recursively enumerable. Okay. So, let us go to the proof. This is the first important thing. I first make use of this thing, of this premise that P is non-monotone. Therefore, there must exist some RE languages L1 and L2 such that L1 is contained in L2, L1 satisfies the property that is P of L1 is equal to T, but L2 does not satisfy the property P, that is P of L2 is false. If P is monotone, this kind of situation can never arise. Since it is non-monotone, I can find at least one counter example to monotonicity, like some language is getting bigger, but the property goes from true to false. Okay. Good. Now, once again, since L1 and L2 are recursively enumerable languages, they are accepted by some Turing machines. Let us call them M1 and M2. So, the language of M1 is L1 and the language of M2 is L2. So, like Rice's theorem part 1, we can take any constant language L1, L2 depending upon the counter example of monotonicity as stated earlier here, right? So M1, M2, these are constant languages, constant machines, and their languages L1 and L2 are also constant languages. So since these are constant machines, their information can be embedded in another Turing machine because each can be specified in a finite amount of space. Okay. So now we are done. If we can supply a reduction from the complement of the halting problem to this pi. So this pi is not same as that earlier pi. I am using the same pi, same notation. So complement of HP to pi. So let us look at this reduction, which is slightly bit more involved than the reduction used in part 1. So yeah, so the reduction engine will embed in the finite control of the target machine N the information of an input for this complement of HP, that is M and W, and these two constant machines M1 and M2. Okay. So like the previous reduction, the input is M hash W, which is an instance of this halting problem or its complement, and the output will be, as you see, it will be single machine N, Turing machine N, such that the language of N satisfies the property P. In other words, P of L of N is true if and only if M does not halt on W. If it halts, then this property is false. If it does not halt, this property is true. Okay. So I will just specify the behavior of N, and again you convince yourself that a total Turing machine can convert the description of M hash W along with these constant inputs M1, M2. A total Turing machine with this knowledge M, W, M1 and M2 can produce a machine N which behaves as follows. Cool. Good. So what is the behavior of N on input V? Again, the output is a Turing machine N. So we should say how it behaves on its private input V. Okay. Now this N is designed as a 3-tape or 3-track Turing machine. Let's say 3-tape. So let's say V is copied or V is presented to N in its first tape. This is not step, this is step, first step. V is copied from first step to the second step. So it's a copy. V is there in both the first step and in the second step. And W is copied from the finite control to the third step. This N will run 3 simulations in parallel on the 3 tapes. On the first step, okay, so this is something like this. Run 3 simulations in parallel. So what does it mean? So in a round robin fashion, N will simulate M1, M2 and M. First one step of M1, then one step, first it will go to tape 1 and run one step of M1, then go to tape 2, one step of M2, then go to third tape, tape 3 and one step of M on W. So this is kept on repeating M1, M2, M, M1, M2, M. Okay. One step each. So these simulations are of this form. On the first step, M1 is simulated on V. On the second step, M2 is simulated on V. Again, this input V. And on the third step, M is simulated on this W. W is the input for M. So, 3 simulations run in parallel. One step of each. M1, M2, M, M1, M2, M this way. These 3 simulations run in parallel. Okay. Then some of the simulations may halt, some may not halt. Then the acceptance conditions for N, this machine, is this. N accepts if and only if one of the 2 following conditions hold. Either M1 accepts V. Okay. So all the simulations are running in parallel. So if M1 accepts V, then irrespective of whether M2 or M halts on their simulations, the other states, this simulation will anyway halt because V is accepted by M1. So if M1 accepts V, there is no need to continue with the simulation. N immediately halts after accepting. Another possibility is that if the third simulation of M on W halts and M2 accepts V, this is the second condition when N accepts. So also you see that if M halts on W, then it knows I will wait until M2 accepts. Okay. If any of these 2 conditions is satisfied, then N accepts, otherwise it rejects implicitly or explicitly, depending upon whether the simulations are looping or not. Okay. So now let us look at what is the behavior of this N. I mean, what is the language which is accepted by N. So let us first look at this. If M does not halt on W, then this condition is never satisfied, and therefore, irrespective of whether M2 accepts or not, the only possible way in which N can accept is by looking at the fact that first simulation on step 1 is accepted. Okay. If M does not halt, this condition is not satisfied. This is an AND condition, right? If this is not satisfied, this 2 is never satisfied. So in this case, N accepts V if and only if M1 accepts V. So if M does not halt on W, the only way N can accept V is by condition 1. In other words, N and M1 in this case have precisely the same language, which is L1. Okay? On the other hand, if M halts on W, then this condition is true, and therefore N can accept V if either M1 accepts V in condition 1 or M2 accepts V by condition 2. In other words, this time if M halts on W, N accepts if and only if either M1 accepts V or M2 accepts V. So in this case, language of N will be precisely the union of the language of M1 and the language of M2. But this is L1 union L2, and since L1 is contained in L2, this union is nothing but L2. Okay. So you recall that for L1 the property is true. For L2 it is false. So if M does not halt on W, property is true. If it does halt on W, the property is false. Okay, and that is precisely what we want to do. Okay. So in particular, if you look at those examples, being an infinite RE language is a monotone property, right? So Rice's theorem is not directly applicable to it. However, if you consider being finite, this is a non-monotone property. Okay, being finite is a non-monotone property, and therefore checking whether a Turing machine accepts a finite set is not even recursively or semi-decidable. Okay, it's a language, the corresponding language of all Turing machines is not even Turing recognizable or recursively enumerable. But we have seen this in the previous chapter also, right? Fin, that is the language Fin. Neither Fin nor the complement of Fin is recursively enumerable, let alone recursive. So this is yet another very powerful statement about Turing machines. Non-monotonicity is required. Other than that, this is quite a powerful and surprising result about Turing machines. Most of the things we cannot do. Yeah, that's the basic idea behind these two theorems. Okay, so this is all about Rice's theorems I wanted to tell, and here are as usual some exercises. So you try to solve all, I would say all, and since we do not think we are going to meet very soon, I will start preparing some solution manuals for this, but please try to solve at least some of these problems yourself. By looking at, I would say, solved exercises, you actually do not gain any insight in how to solve problems. So please try solving at least a few of these exercises. Okay, so let me stop. This is all about Turing Rice's theorem that I would like to say. Next time I will talk about non-deterministic Turing machines and their implications. So see you.